So I'm going to cover now the case where we have fluid flowing through a tube here, where at the boundary we have a constant surface heat flux. Okay, so if we have a moving fluid in here coming in with a mean inlet temperature and exiting with a mean outlet temperature, okay, well, if we know our heat flux, then one thing we could do is to solve for one or both, a combination of these mean temperatures, right? So usually we use this to solve for the mean temperature at the outlet. Okay. One other unique thing about this is if we wanted to solve for the temperature at any location x, we could rearrange and say that the temperature at any location x equal to the mean temperature coming in plus our heat flux times our perimeter over our mass flow rate times our heat capacity times distance x. Now, if we have a constant surface heat flux and laminar flow, okay, then our Nusselt number is equal to 4.36. Okay, this is, I should also mention that this is fully developed flow. Okay. And we can use this to then solve for our convection coefficient. We could then use that, okay, in conjunction with this constant surface heat flux, let's say, to solve for the temperature at our surface at any location x minus our mean temperature at any location x, okay, using the combination of equations that I outlined here, right? I find my mean temperature at x here, okay? I find h bar from here. I can rearrange then to solve for my average surface temperature. Okay. If instead I find that I have developing flow, okay, I can come to figure 8.10b for the combined entry length problem. Okay. And my average Nusselt number I can get by solving for my inverse Grates number, okay, which is equal to x over d divided by my Reynolds number times my Prandtl number. Okay, where for the average Nusselt number, this value of x is equal to L. Okay. For the thermal entry length problem, we're going to use equation 8.57. Says that the Nusselt number, the average Nusselt number, is equal to 3.66 plus 0.0668 times this Greats number divided by 1 plus 0.04 times this Greats number to the 2/3 power. Okay? Or again, we're going to use L in place of X. If you want local Nusselt numbers for either case, which could be true. So instead of solving for maybe an average surface temperature and an average mean temperature and using H, I should have specified before that this was a local convection coefficient. If I want an average surface temperature, I can use this expression. So to find a local Nusselt number, I can use figure 8.10a. Okay. And then finally, if I find that I have turbulent flow, what I can use is the following. My Nusselt number is equal to my friction factor divided by 8 times my Reynolds number minus 1,000 times my Prandtl number divided by 1 plus 12.7 times my friction factor divided by 8 to the 1/2 power times my Prandtl number to the 2/3 power minus 1. Okay. And again, this is for turbulent, fully developed flow. If the flow is turbulent in this class, we're just going to consider it to be fully developed right off the bat. So really, you only need to worry about these expressions when you have laminar flow.